So let's see now in this session how the principal components are calculated and how the results are interpreted. Okay, so let's say that we have p variables, input variables, and what we want is to calculate m principal components with m smaller than p, such that this m new variables summarize most of the variability of the input data. So each one of these new input output variable will be a linear combination of the input ones, and so it will be, for instance, the first principal component will be collection of numbers multiplied by each one of the input variables, and there is a constraint on this linear combination that it has to be a unitary transform, so that the norm of the vector is 1. Okay, so the new variables are called principal components. The coefficients used to construct the linear combination, they are called the loadings, and then the specific projections of input data. So this is individual I, so we have the observation for individual I of the first input variable, second and pth input variable. So we project it and then we get a value, and this value is called the component score. Okay, so the point is how to calculate these coefficients, these factor loadings. And the thing is that for each of the input variables we have to subtract the mean, and then we compute the covariance matrix, and then we diagonalize that matrix computing the eigenvalues and the eigenvectors of that matrix, and we sort them with respect to the eigenvalues. So the higher eigenvalue occupies position 1. And then the corresponding eigenvectors are the coefficients that we need to use for the linear combination. So let's see some examples. So let's say that we have two input variables that are the minimum and maximum temperature. So here we have a plot, and we see that there is a strong relationship between the two. So we follow the procedure described above. So we compute the mean or the average of the minimum temperature, the average of the maximum. We subtract. Now we have a new variable. Let's call them Tmin prime, Tmax prime, and then we compute the covariance of these prime variables, and then we compute the eigenvalues and the eigenvectors. So here we have the eigenvalues. So there is a very strong difference between the two eigenvalues, and those are the eigenvectors. So the eigenvector associated to the first eigenvalue is this one, the one associated to the second one is this one. Eigenvectors, they have the property of being orthogonal to each other, so the new variables will be uncorrelated to each other. And then if we construct this new set 1, set 2 variables, so the first and second principal components, what we have, so to calculate the first principal component, here are the loading. So it will be 0.57 times the minimum temperature plus 0.81 times the maximum temperature, and these and the same for the second principal component. So if we transform every input point into the new set of variables, this is the plot we get. So now we see that the two principal components are uncorrelated, so that is a cloud that is aligned with the xy axis, so that is the indication that they are independent. Not independent, the condition is uncorrelated. That is a little bit less stringent than independence. Okay, so and there is also an important thing that it is a rotation. So this transformation, the principal component analysis transformation, is just a rotation of the data. So we can identify a few points. So for instance, this one and this group are these ones and this group. So it is a rotation and a mirror of the input data. Then if we calculate the correlation, the covariance matrix of the new variables, the PC1, PC2, they are uncorrelated because the off-diagonal terms are 0. And actually we may notice that the diagonal terms that are the variance are equal to the eigenvalues. So actually the eigenvalues of the covariance matrix are the variances of the new components. And the sum of the variances of the P principal components is equal to the sum of the eigenvalues. And let's see some more examples. So PC1 calculated in this way, so with these factor loadings, is somehow related to the mean. So we can summarize the minimum and maximum temperature by just computing the average. So the average here is represented in black, and the principal component is represented in green. And we can make a plot of the average and the first principal component, and we see that they're very much related, but they're not exactly the same. Actually, PC1 has a little bit more information than the average. And this is so by construction. So PC1 is the variable that has maximum amount of variability. So there is no other linear combination of the input variables that has more variability than the PC1 we have just constructed. So the first eigenvector is really the optimal combination of the input, linear combination of the input variables such that the variability of the output is maximized. So we are not, in general, if we have P input variables, we will have P output principal components, but we are not interested in all of them. So we would like just to keep a few of them that summarize the data in a good way. So how much information are we losing by removing the last principal component? And we can have access to that information by the analysis of the variance that is kept. So the total variance in the input variables, assuming that they have been centered around 0, so this would be the prime variables I was referring to at the beginning, would be the sum of the sum over all variables. This is the sum over j of the variance of each one of the variables alone. The variance explained by one particular principal component is the sum of all these projections, of all the projections of the input data onto that principal component. So just a reminder, using these factor loadings, we can calculate set 1, we can calculate set 2. So the variance of set 2 is projecting the input data using these loadings, and then we will have the set 2 components, and then we can calculate the sum of the squares of these set 2 components. And this is what is done here for the mth principal component. So here we have the sum over all the observations of the projection of the input data following that eigenvector and then squaring. Then the proportion of variance explained by the mth principal component is just the ratio between these two numbers. So this is the total variance, this is the variance explained by the mth principal component, and the proportion that this one is explaining is the ratio between the two. So here we have an example of those ratios. So let's say that we have some data set for which the first principal component is explaining about 60% of the variability, the second one is about 30% of the variability, and then the rest, they have a much smaller share of the input variability. So we want to keep the minimum number of principal components such that most of the variability is kept. So what is most? That depends on the problem. So here with just 2 components we are keeping 90% of the variability, and 90% is normally considered to be enough, so the rest should be more or less noise. And here we have another example where only one component has 90% of the variability, while the other ones, while the rest has only 10% of the variability. And here is a different example in which all the inputs are uncorrelated, so there is no correlation between the input variables, so the principal component analysis cannot compress that variability into a few variables. So we see that all the principal components, they have more or less the same amount of variability, and it is not easy to choose the minimum number of principal components that we want. Here we have the proportion of variability explained by each variable we can accumulate, and this is this plot, red plot that we have here, that is called the scree plot. So both together they are called the scree plot, and the point is to find an elbow in this scree plot. So here there is a very clear elbow, here too. So the first two, they explain much of the variability, while in this other plot it is not easy to find that elbow. Okay, so then regarding the principal components and the loadings, we can have 2 different kinds of principal components. The first one is called shape type. So the shape type, so a shape principal component is one in which all the factor loadings, they have different signs. So you see positive and negative loadings, while the size type of principal components, all the loadings have the same sign, either positive or negative. And those principal components, the size types principal components, they can be considered to be weighted averages of the original variables. So PCA is relative to the location and to the variability of the input data. So if you have a variable that is in the order of 1000 and if the other one is in the order of 1, then the one in the order of 1000 will dominate, especially the variability. If one of the variables has much more variability than the other, then that one will dominate the analysis. And for that, it is typical to standardize the data so that we divide by the standard deviation of each one of the input variables, and then so these x prime variables that are the transform variables before doing the PCA, it is not only that we are subtracting the mean, but we are also dividing by the standard deviation. And then by standardizing the input variables, what we are analyzing is the correlation structure between the variables and disregarding of their internal variability. Then another very useful tool that we have with the PCA is the B-plot graph, in which we can see the projections of the input data to the first and second principal components. These are these dots, but we can also plot at the same time the projection of the input variables into this plot. So for every input variable we can analyze the loadings. So if we are plotting component 1 versus component 2, then we would take the first loading of the first input variable in both components. So this is the first variable, so it would have 0.4 in the first principal component and 0.6, let's say, in the second. So this would be 0.4, 0.6. It would be this point. And the same for x2, that is here. x3 has 0.4 in the PC1 and 0 in PC2, so it is here, and the same for x4 and x5. So in this way we can recognize groups of variables. So x1 and x2, they are correlated to each other, they are bringing almost the same kind of information. The same happens with x4 and x5, and x3 is an independent input. Let's see some examples. So let's say that we have 5 variables, input variables, that they are uncorrelated and they have the same variance. So we are constructing the input variables like this. Here we have the scatter plot, a matrix scatter plot between each pair of variables, the covariance matrix, the correlation matrix. Everything is as expected. So most of the correlations here are very close to 0, they are not significant. And then when we do the PCA analysis, we see that most of the eigenvalues, they have so all of the eigenvalues have similar values, and the small differences are caused by just random sampling. So just by chance, x1 happened to have a little bit more variability than the rest, and then these sampling errors, they turn into small differences in the eigenvalues. And so here we have the covariance matrix of the principal component. So they are orthogonal to each other, and the variability of each one of the input variables, of the output variables, is almost the same. So here we have how the input variables look like. So we have a few samples of these input variables, and then we can reconstruct the data. And we have not seen this, but we can approximate x. So the x observations that we have here, so these x observations, we can approximate them by a sum of the set variables of the principal components, so that we can get closer and closer to the input observations by adding more and more principal components. And so here is how the reconstructions look like. So the more and more principal components we add, the more the closer we get to the input, so that we see that in this example, because of all the input variables were independent, then we need all the principal components to get a perfect reconstruction. And in the B plot, we see that we cannot group the input variables. They are totally away from each other. The further from each other that they can get in a two-dimensional plot. And let's see a second example. So in this example now, we have also 5 input variables, but now they're very much correlated to each other. The correlation between the every pair of variables is around 0.9. So we see that x1, x2, x3, x4, they all have almost the same information. And now the screen plot gives almost 90% or 95% of the variability just concentrated in one principal component, and then the rest is just kind of noise. we can see also in terms of covariance the huge difference of the eigenvalues. And now we can very easily reduce the dimensions of the input data. So we have the first principal component is a weighted average with almost the same weight for all the components, because they all bring the same information, almost the same information, so they get equal weights. And then the rest of the principal components, they are rejected simply because they explain very little variance. So it is not it is an overfitting exercise to try to explain them. Okay, so here we have the reconstruction of so we have the input variables, they are bringing almost the same information, and then the reconstruction with just one principal component that we see that it is almost the same as the input one, and by adding 2, 3, 4, 5 principal components, we get closer and closer to the input, but already the first principal component was a very good approximation. Then we can see here the variables projected onto this B-plot. So the first principal component takes all the variability, and we see how they cluster here. So x3 and x4, they are almost the same. x1, x5 and x2, they are a little bit different from x3 and x4, but actually this is an over-interpretation. And the reason is that there is so little variance in the second component, the second principal component, that trying to interpret things around that or that reason along that component is really overfitting. So if we look at the first principal component, all these variables, they get projected onto the same point, meaning that they are almost all the same. Here we have another example. At the end we will see how this example has been constructed, but let's for the moment look at the different input variables, the scatter plot. We see that some of the variables are very much related, for instance x4 and x5, or x1 and x2, maybe x3 a little bit less than x1 and x2. And then we can see here the covariance, the correlation, and the scree plot here clearly shows that two components are normally enough to represent this data. Then we will keep only the first two components, and the first component is a weighted average, the second component is a shape component. Then we have the input variables, we have the reconstruction from the first and second principal components, and they are not exactly the same as the input, but they represent very well the input data. And then in the B plot we can see here that x1 and x2, they are very much correlated to each other, x4 and x5, and x3 is a little bit independent. So here we have the input data, and now we are revealing how this data was generated. So we had different sine curves. x1 and x2, they were very much related to each other, they were not exactly the same, and that is why they don't get one on top of the other, while x4 and x5, they were very much related. So here we have x4 and x5 together, and x3 was kind of somewhere in between. So that is the reason. So we generated first these sinusoids, and then we added noise, and then we submitted to principal component analysis. So we can see that principal component analysis correctly identified the structure of the generation of the data. So this would be all for the principal component lecture, and see you next time.